Good afternoon, Professor Laine, and thank you for finding the time for this short interview. As a cost action, we always try to share the words and thoughts of professors, but also participants taking part in our cost action. The first question that I would like to ask you is about how did you end up in the field you are working in? So how did you get attracted from protein structure, protein dynamics and functions, and how did you first found this field, and why are you motivated in keeping with this?
So good afternoon. Thank you very much for giving me the chance to speak. So I got interested into protein structures actually during the engineering school. So I had a teacher. I remember during his course he was saying that not so many students are attracted by protein structures. So I was at engineering school. I was studying bioinformatics. It was fairly recent at the time. And I thought, well, let's just help him because there are not so many students interested. So let's just go to this field. And this was maybe the first motivation for me. And then during my PhD, I worked with a system that was dynamic. And actually it was the dynamics of the system was dependent on the calcium ion load. So I was mostly doing molecular dynamics simulations and also during the postdoc. And then when I got recruited as associate professor, I got interested more into the evolution of protein and protein sequences. And so I think it's very nice because now I can combine both aspects and I think they are complementary. So yeah, this is how I ended up here.
How you started. So you would say it's a mixture of interest plus a few competitors at the time.
Yeah, maybe a mixture of interest and a bit of chance. Yeah, of course. I wouldn't say I had planned everything from the beginning. It's a bit of random choice and also interest in these objects. And I don't regret it. So I think these objects are fascinating. So
all right. Machine learning for non-globular proteins as a cost action is focusing on non-globular proteins. And oftentimes non-globular proteins drift from this paradigm of structure and function. What do you think is making them challenging as a study subject, or from another perspective, exciting?
Mm-hmm. Well, I think they're very exciting, especially now that we have, after the breakthrough in protein structure prediction, pretty much the common idea is that the problem of predicting structures of single proteins of monomer is solved, but these proteins are intrinsically challenging because they don't adopt typically a well-defined, well-folded, well-stable structure. So I would say they are even maybe more interesting or more exciting now because it's clear they're challenging with respect to the state of the art, which has advanced a lot in recent years. So then I would say that still it's probably we should think of this as a continuum. So non-globular proteins, you have also these aspects of dynamics that are very important and different sequence dynamic function relationship in several parts of proteins. So I guess you can be a bit more general about the way you see this. So why they're challenging also because of their nature, but I think because also of the lack of data, of lack of validation data. So maybe it's also very nice for creativity because then we can still think about new methods to approach the problem. We have many signals that we can detect. We don't know if they're real or not. As long as the data are not there, in a way, it's also stimulating for the imagination, let's say.
Yeah, I agree. Actually, some of your works are focusing on predictors and variance predictors. And some of these predictors are either using sequence-based information or structure-based information. And in the case of non-globular proteins, as you said, there is not much data, or some structure predictors are not doing that well in this context because they are non-structured proteins. So how do you see the field evolving, or how do you think scientists are going to tackle this problem?
Mm-hmm. Yeah, so it's clear that, from the perspective of variant effect prediction, what we've seen in recent couple of years with the explosion of structures, of predictions of structures thanks to AlphaFold, there's been a real push to try to exploit these structures to improve variant effect prediction. So of course, when you don't have a well-defined structure, you can't use this. But what is also interesting is to see that the contribution of these structural information is not that much, even for globular proteins that have a well-defined structure. So I would say it really contributed to improve the prediction of the impact of mutations on thermodynamic stability. But for other phenotypes like organismal fitness, you don't really see a big contribution from structure. That's the first point in general. And then specifically when you don't have access to structure or where it's very dynamic, well, I think the common view has been that intrinsically disordered regions tend to be more variable in evolution, so they have a weaker signal in terms of what you can capture. So let's say one ingredient that is really useful for variant effect prediction is evolutionary conservation, right? So you look at what are the mutations that are basically permitted by evolution that often occur, and those that are rare will typically be impactful or deleterious. And so this is more difficult to capture with intrinsically disordered or non-globular proteins because in the case of disorder, typically you will have high variability, so weaker signals. If you think of in terms of repeat proteins, you will have problems with the alignment, for instance, putting things in front of each other. But still, I think there is some signal to dig here that is maybe underexploited yet so far. So if you don't look at the absolute conservation, but you look at things a bit more relatively, you can see that there are different levels of sensitivity, of mutational sensitivity or evolutionary conservation, and you can capture subtle changes. So I think this is still one direction that we should maybe go into, investigate. There is also there are promising avenues from the protein language models, although in the end, I think now we start to have some experience with these models, and what we can see is that they are not totally compensating for the lack of information in sequences, right? So they don't work that well on disordered regions. They don't work that well on viral proteins. So when you're not able to build an alignment that contains enough information, typically the language model is also going to have poor performance. So I would say we need to have more careful identification of signals in the sequences. And then, of course, we need to also go for ab initio methods for simulating these conformational ensembles and the different conformations that they can adopt. So I think this probably is also a way to go that is still underexplored, also because it's very computationally demanding to really simulate the behavior of these proteins.
Mm-hmm. On a different side, or on a different argument, about initiatives that can tackle problems that are bigger than what a single lab can do. What is your take on European initiatives in terms of research coordination and research guidelines? Mm-hmm. And what is your opinion on European initiatives like, I don't know, COST, mm-hmm. but it can be also Horizon initiatives?
So I would say that in general, I'm very positive about this initiative. I think there are great opportunities to exchange. So if I take the example of the cost action ML, I mean, it's been, so I think it's my second conference in this cost action. And every time it's very rich, the exchanges, and I meet new people and I can have nice interactions. And then I have also ideas. I come back to the lab and I can follow different leads. So this is really rich, and I think it's really nicely organized, and we can get a lot of feedback for the research. Then, I mean, other European programs are very good way to get your research funded and to be able also to scale in terms of what you can do. And also on the, let's say, teaching aspect, so at the university we have this example of, thanks to the EU Plus initiative, we could kind of build a network of different masters in bioinformatics across European universities, and this allowed us basically to build 2 courses that are collaborative between these universities, and so we meet regularly, we exchange together, and it also reflects on the research, because then when you know more your colleagues for the teaching parts, you start to exchange about research, and then you also get potential collaboration. So I think and also for the students, this is typically very positive experience to be able to interact with students from other universities. So I think it's really beneficial, and it's kind of unique and special. You don't really have equivalent otherwise. So,
I mean, nowadays the role of teachers, it has to be complicated, especially considering the speed at which language models or in general algorithms are developing.
So I don't know, because in a sense, but this is also true for research, right? The pace is very, very rapid. So yeah, you can feel that it's going too fast, and then it's going too fast actually for the knowledge to be digested and to be packaged in a way that you can actually teach it. But in some other respect, there is a real democratization of many aspects of AI, for instance. And so also for teaching, the teaching materials are more abundant, more accessible, and also the tools that you can use, what you can do in classrooms now with the notebooks that are accessible, let's say just for running MD simulations. You can do this in a class now, you couldn't before because you had to install packages and then you had all these technicalities. So at the same time, it's also easier to adapt, I would say. So it's not, and it pushes us also to not be, left on the side. So this is also beneficial, I think, for teachers to be a bit pushed to update, and then it also profits the research. So
you're not limited to the hardware anymore as it was, 15 years ago.
Yeah, you mean for transmitting the knowledge?
Yeah.
Yeah, I mean, things have become more accessible. So at the same time, it's sometimes a bit difficult to identify where is the good balance between being able to touch a lot of subjects and make the student try a lot of things and then go deep into problems. And of course, there is the question of how they interact with large language models, how they use these new tools. But overall, I think it's a stimulating time also for teaching.
Mm-hmm. All right. I think this is going to be valuable both for researchers and students and teachers. So thank you for finding the time.
Thank you.
I wish you good luck for your future research.
Thank you very much.